Hello everyone. This video will cover sections 7.2 and 7.3. Last time I covered sections 6.3 and 6.4. Now we haven't covered 6.5. We only need one very simple result from 6.5, and it's the following. So from 6.5, if you have two random variables that have the same moment generating function, then that means they have the same distribution. Okay, so because moment generating functions are unique, so moment generating functions, which we talk about this in detail in the previous chapters, are unique. Okay, so therefore, if you can identify the moment generating function, then you should know what the distribution is. Now recall that the moment generating function for normal distribution, so let's say that x is normal with mean mu and variance sigma square, then the moment generating function for this, which by definition is e, the expected value of e to the tx, this is equals to e to the mu t plus sigma square t squared over 2. So this is the moment generating function in general for a normal distribution. So any function that has a moment generating function that looks like this has to be a normal distribution. And this is very important because the whole chapter 7, is going to be about the normal distribution. So let's say that we have a new variable u, where this is y1 and y2, and let's say y1 is normal mu sigma square, and so is y2. Okay, so they are independent and identically distributed. Okay? So what will be the moment generating function of u? So notice that, well, by definition, this will be the expected value of e to the t, and then y1 plus y2. Right, so notice that this will be equals to the expected value of e to the t y1 times the expected value of e to the t y2, okay, because they are independent. And then this will give you e to the, let's say, mu 1t plus sigma square 1t over 2 times e to the mu 2 t plus sigma 2 squared t over 2. And then using basic properties of algebra, this will be e to the t. You can factor the mu 1, the mu 2, and you can also factor the t over 2 here, and it will be sigma 1 square plus sigma 2 square. Right, so this gives us a very, very important and useful result. So this automatically implies then that u has a normal distribution where the mean is mu 1 plus mu 2 and the variance is sigma 1 plus sigma 2. So this is a very, very useful result. In fact, this isn't true in general. So if you go up to 10 or 20, doesn't matter what's the value for n, you will get a normal distribution where the sum of the means and the sum of the variances. Okay? So we need this for the stuff we're going to do in this section, and this result will be applied automatically to the first term. So the first term says the following: let y1, y2 all the way to yn be a random sample of size n from a normal. Okay, so we know it's from a normal distribution where they have a mean mu and variance sigma square. Then we're going to define y bar. Y bar, by the way, is called a statistic, and we will show right now that y bar has a normal distribution where the mean is mu, and the variance will be the variance divided by the square root of n. Okay. Now, using this fact right here, okay, that if you add a bunch of normals, the distribution is still normal, it's very easy to show this. So for example, the expected value of y bar, which again by definition this is what we call it mu y bar. This is 1 over n, the expected value of y1 all the way to yn, which is equals to 1 over n. The expected value of the first one is mu. All of them will be mu because they are identically distributed. We have n of this, so this will be n over n times mu, which is just mu, which is what it says here. Then to find the variance of y bar, this will be 1 over n squared. We're using the definition of variance. And this will be times the variance of y1 plus the variance of y2 all the way to yn. So this will be 1 over n squared, and then you're going to have n variance here. Remember, all of this, the variance is sigma squared, so all of these are sigma squared, and you have n of them, so this will be sigma squared over n, which shows this. Now, because we already know that if you do a sum of normal distribution, it will still be normal because of the result from here. So then this implies, therefore, the y bar is normal where the mean is mu, and now the variance is this sigma squared divided by n. Alright, so now this implies, because remember you want to use a calculator to find these values. Most calculators and most tables only give you the standard z values. So that means you define z to be y bar minus mu of y bar divided by the standard deviation of y bar, that this will be a standard normal, and you can pretty much write this like this: y bar minus mu. This will be sigma divided by square root of n, or it may be easier to write it like this. It's easier for computational purposes. So this will have a standard normal distribution. Right, so by that I mean this is normal, the mean is 0, and the variance or the standard deviation is 1. Right, so let's do an example of this. Remember, since this is a standard normal, all you have to do is technically use either the table or the calculator to compute the values. So just keep that in mind. So here's the example. Assume that the amount of fuel dispensed by the battery machine is normally distributed with sigma equals to 2. Okay? Now, let's say that, let's call this part A. Let's say that n is equals to 9. So you have a random sample of 9. Okay? So what is and let's say we're interested in the probability that the absolute value of y minus mu is less than or equals to 0.3. Okay? Remember that this is the same thing as the probability that minus 0.3 is less than y bar minus mu is less than 0.3. Okay? Remember that we know that z, you define it to be this, you will have a standard normal distribution. So here, this is not quite that, but this is equal to this part. So if we multiply by the square root of n and divide by sigma, then we would end up with z. So therefore, if you do the square root of 9 times 0.3 divided by 2, this will give you a 0.45. So therefore, what we're trying to find is what's the probability that minus 0.45 is less than z less than 0.45. Okay. And then if you draw a table, so you have 0.45 here minus 0.45 here. So this is what you want. So you look to the table from the book. The book says that this area right here, this area in black for 0.45 is equals to 0.3264. Remember that this is what we want. We want this area. Notice that from here to here, this has to be 0.5 in terms of area. So if you do 0.5 minus 0.3264, this part right here, this, let me use a different color, this part in blue, is equals to 0.1736. Why? Because this plus that has to equals to 0.5. Now by symmetry, this will be the same value. You can also use a calculator if you want to make this easier on you. So technically the area, you can see that it's obvious that it should be this plus that. So this is twice 0.1736 or 0.1736 twice. So this is 0.3472. Now let's do the same thing, but let's say n was 64 instead of 9. So we still have the exact same problem. The only difference is the value for n. Okay. So here now we have the square root of 64, which is a times 0.3 divided by 2, and that will give you 1.2. So therefore now we're trying to find what's the probability that minus 1.2 is less than z less than 1.2. And if we do the same thing with the table, you have 0, 1.2. You look to the table for 1.2, the table says this value is 0.1151. Remember that what you want is actually this part. You want this and this between minus 1.2 and 2. And just like the previous problem, this plus that has to equals to 0.5. So 0.5 minus 0.1151, it gives you 0.3849. So therefore this will be twice 0.3849, which is 0.7698. So notice that as the value for n increases, well, the probability increases. Okay, so note as n increases, then the probability increases too. Okay. Right, so let's try another example. So let's say that y is normally distributed with a mean of, let's say, 270 days and standard deviation of 20 days. Okay, so this will be like the length of a human pregnancy. Okay. So if you take a sample of these identically distributed values, so let's say that n is 25. So remember here, mu is 270 and sigma is 20. So let's say that y bar, as you know by definition, it will be 1 over 25 y1 plus y2 of the way to y25. So what will be the probability that the average of a human pregnancy of a sample of 25 will be more than, let's say, 272 days? Okay? So remember, z is equals to the square root of n times y bar minus mu divided by sigma. So in our case, it will be the square root of 25. It will be 272 minus 270 divided by 20. So then this will be 5 times 2, so that's 10 divided by 20, that's 0.5. Therefore, this is the same thing as the probability that z is greater than 0.5. And if we look to the table, you have 0.5. So for 0.5, this value, which is now, this is the part that we want from the table, this is 0.3085. And that will be the probability that the average will be more than 272. Alright, so let's look to the next part. The following theorem says the following. We have the same assumption: y1 to yn are randomly distributed normal variables with mean mu and variance sigma squared. We already know that these are standard normal. So this is a new thing. If you square these values, then this will have a chi-square distribution with n degrees of freedom. So make sure you keep track of the degrees of freedom. Okay? So now the chi-square distribution is not symmetrical. The graph looks like this. Okay. And the table, which I'll show you right now, it gives you usually the area to the right, which is defined by chi-square alpha. So this part is alpha. So what this means is that the probability that chi-square is greater than chi-square alpha is just equals to alpha. Okay, so for example, let's say you want to find the probability that the sum from I equals to 1 to 10 of ci squared less than equals to some b gives you 0.9095. Okay. Right, so here you have to be very careful, okay? Because the table only gives you the area to the right, and it is asking you the area to the left. Okay, so this is what I mean. This one is telling you, okay, find a value of b where this area is 0.95, which automatically implies that this one has to be 0.05. Okay, so remember that this one is has a chi-square distribution where the degrees of freedom is equals to 10, because that's the value for n. This is an example of a chi-square table. This is not exactly the same one you have on the back, but all of them give you the same answer. So here, remember that I told you this only gives you the area to the right, which is clearly right here, and you want the area to the left to be 0.95. So that means that you are really looking for the area to the left, for the right to be 0.05, and you have 10 degrees of freedom. So since we have 10 degrees of freedom on the table, just go to 10, which is here. And then you want the area to the right to be 0.05, which is this one. So the value that you're looking for is 18.307. So therefore, this implies that the value for b 18.307. Okay, so notice that this is equivalent to saying this: the probability that chi square is greater than 18.307 is the same thing as 0.05, or this is the same thing as saying that the probability that chi square is less than 18.307 is equals to 0.95. Both of them are the same thing. The thing you have to be aware or careful is that the table only will give you the area to the right. Now you can use a calculator like the TI-83 or 84 to find these values too. So you want to know how to do that instead of the table, just come to office hours or ask me during class. All right, let's look to the next theorem. The theorem says the following. Is the same assumption as the previous one. Let's say that y1 all the way to yn have a normal distribution with mean mu and variance sigma square. So then if we define the following n minus 1 s square over sigma square to be 1 over sigma square times the sum from I equals to 1 to n of yi minus y square, then this has a chi-square distribution with, and this is very important, this is a big distinction between this and the previous one. This one has n minus 1 degrees of freedom, okay, so that's very important. And also y bar and s square are independent, where s square is called the sample variance, and this is equals to the sum of yi minus y bar square divided by n minus 1. These two statistics are going to be very useful, or actually the whole class about inferences, which is, I think, is 381. It's just about these two statistics most of the time. Okay. Now, the important thing here, what we care here, is that this has a chi-square distribution, and be careful that this one is n minus 1 degrees of freedom, while this one has n degrees of freedom. Okay. Right, so let's do the following example. Let's say you want to find the value for b such that this probability is true. Okay. Let's say that this is 0.975. Let's say here the value for n is 20 and the value for the variance is 1.4. All right, so this implies that, remember that you need to have n minus 1 s square over sigma square in order to have a chi-square distribution. Okay? So if we multiply both sides by 19, so this is the same thing as the probability you have 19 times s squared divided by 1.4. This should be the same thing as less than 19 b over 1.4, and this should still give you the same probability. So then if we look to the table, which we have here, but now we have 19 degrees of freedom. So 19 is this one right here, and you want the area to the left to be 0.975. That means the area to the right has to be 0.025, which will give you this value right here. Okay, because remember, this only gives you the area to the right. So this one is saying the area to the left, it's pointing to the side, is that. So that means the area to the right has to be 0.025. So therefore, this implies that 19 over 1.4b has to be equals to this value, 32.52. So this is 32.852. And then you solve for b, which is basic algebra. then that means B would be 2.42. So you should check on this. All right, so note that this is technically also the 97.5 percentile, so this value for B. And also notice that if I could ask you to find the probability that a square is greater or equals to B is equals to 0.025, that the answer still going to be B equals to 0.42. Okay, haven't changed anything. Okay, now let's look to what happens if you combine standard normal with a chi-square, which remember chi-square comes from the normal anyways. So we have the following definition. If Z is a standard normal and W is a chi-square with no degrees of freedom, okay, then if Z and W are independent, the T distribution, which is sometimes called a student T distribution, is defined to be Z divided by the square root of chi-square, and that itself divided by its own degrees of freedom. All right, so here nu is equals to n minus 1. Remember, this is the degrees of freedom. All right, so remember that if w chi-square is chi-square, remember that w is equals to, therefore, n minus 1 s squared over sigma squared. So if you divide by n minus 1, well, obviously the n degrees of freedom will cancel, and you'll have only s over sigma squared. Then if you take the square root, then this will give you s over sigma. So therefore from here t will be the square root of n y bar minus mu divided by sigma, and then if you divide by the square root of w, then this will be sigma over s. So notice the sigmas cancel, and you end up with t is equals to the square root of n y bar minus mu over s. And notice the similarity between this and z. So you're essentially just replacing the standard deviation with the sample standard deviation. Now, there is a lot of similarities between C and T. The normal distribution, as you know, looks like this. The standard normal, remember the mean is 0 and the standard deviation is 1. So this is, say, Z. T is going to have a similar shape, but it's going to change depending on the degrees of freedom. But no matter what, the mean is always going to be 0. So these are different values for T. So the mean is always going to be 0 too, but the variance is going to be always more than 1. Now to read the T table, you read it very, very similar to the way we read the chi-square table. So the table looks like this, symmetrical. So the table will give you this: the probability that T is greater than T alpha will be equals to alpha. So if this is T alpha, this value is alpha, which means again it gives you the area to the right. Now this is how you read the table. Let's say the question is asking you to find the value of B such that the area on the right side is 0.025, okay? If the degrees of freedom is equals to, I don't know, 9. So then you just look to the table, look for 9 degrees of freedom, which is here. And then you want the area to the right, okay? So you essentially, this is what you have. you're trying to find the value for B, so that this area is 0.025, and 0.025 is here. So for 9 degrees of freedom, that will be the value 2.26. So therefore, that means that B is 2.262. Okay. Now, just like the chi-square distribution, remember that this will be essentially the same thing. If I ask you to find the probability that T is less than B, well, it will be 0.975, which will be the 97.5 percentile. Okay, this will give you exactly the same thing, because if this is 25, that means this is 97.5. So therefore, the value for B will also be 2.62. Now, just in case that was not completely clear, let me do one more. Let's say that you want to find the probability, the value, that the probability that T is less than that value, that is equals to 0.990. Okay? So then this is telling you that the area to the left of B, this area, is 0.90. So that means that the area to the right, which is what you will find on the table, is 0.10. And let's say that the degrees of freedom is equals to 15, which, remember, that means that n was 16. So then just look to 15 degrees of freedom, which is this line right here. Then you want 0.10, 0.10 or 100 will be the very first one. So that will be 1.341. So that means that B is 1.341. And don't forget that this is essentially saying that T of 0.10 is equals to 1.341. All right, so the last relationship we're going to see in this section is called the F distribution. And essentially, it's just the ratio of two chi-square distributions. So notice that F is defined to be a chi-square divided by his own degrees of freedom, divided by another chi-square divided by its own degrees of freedom. Okay? And this one obviously is in the numerator, so we will call this the numerator, and this is the denominator. So if you simplify this a little bit more, this will be S1 squared divided by sigma 1 squared, and this will be S2 squared divided by sigma 2 squared. So notice that if they have the same standard deviation or the same variance, the F will become just S1 squared over S2 squared. Okay? And here nu 1 is the degrees of freedom of the numerator, which will be whatever n. So this case will be n1 minus 1. In E2, there will be degrees of freedom of the denominator, and there will be n2 minus 1. Now, the F table provided at the back of the book is pretty annoying, so there is a better table, which I can post on Beachboard later, but this is what I mean. Let's say we want to find the value for B such that S1 squared over S2 squared doesn't equals to B, that this will give you, let's say, 0.95, and let's say that N1 is 10 and N2 is 7. So therefore the degrees of freedom for the numerator is going to be 9, and the degrees of freedom for the denominator is going to be 6. So this is the table that I think is much easier to read than the one on the book. So therefore here, assuming the sigma 1 is equals to sigma 2, remember this has a F distribution, okay? And to read this table is much easier than the one in the book, so here it is. So the degrees of freedom for the numerator is 9. So from left to right, you have the degrees of freedom for the numerator, and up and down is the denominator. Well, since there is no 9 here, let's say that, let me change this, let's say that this was 9. So therefore this will give you 8. So then you look to 8 degrees of freedom, which is here, and then 6 for the denominator. Okay, so the answer has to be in here. And then since we want the area to the right, by the way, the shape of this graph is technically like chi-square, looks like this. So in our particular case, we want the area to the left to be 0.95. So that means that this one has to be 0.05. So therefore, just look for 0.05 in here, which is this value. So the number will be 4.15. And that's how easy it is to use this table. So again, in other words, what this means is that the probability that F will be less than or equals to 4.15 is equals to 0.95, or the probability that F will be greater than 4.15 is 0.05. Right, so that's it for section 7.2. So now we're gonna go to 7.3, which is in essence one of the most important things in the whole class. So remember the y bar will be normally distributed with mean mu and variance sigma squared over n if y1 to y2 and so forth to yn are itself normal mu sigma squared. Okay? Well, we will see that even if they don't have this distribution, what about the distribution is unknown, under some specific conditions, then y bar still will be normal, and that's one of the biggest results from the class, which is actually one of the most important things for statistics, and it's called the central limit theorem. All right, so let's talk about the central limit theorem. So now we already show, okay, so we show before that if y1 is normal and y2 is also normal, whatever it is, that y1 plus y2 is still normal, and more importantly, y1 plus y2 over 2, which is the mean, is also normal. However, this is not true for other distributions. If you recall what we did in chapter 5, in chapter 6, to find the distribution of more than one variable, for example, let's say that if y1 is Poisson with lambda 1 and y2 is Poisson with lambda 2, you should check, or you probably have one of these problems already in the homework, that y1 plus y2 is not Poisson anymore. Okay, so when you add to a Poisson, you don't get another Poisson, but if you add to normal, you still get a normal. Actually, if you add two exponentials, it's not exponential. If you add two gammas, you don't get another gamma, and so forth. And even worse, y1 plus y2 divided by 2, which is the average, is definitely not Poisson. Okay? However, there is a way where it doesn't matter which distribution you have, the y bar will have a normal distribution, and that's kind of like doing magic, but that's what the central limit theorem does, and it says the following. So suppose that you have y1 to yn, and they are IID, which remember it means independent and identically distributed, where the mean is mu and the standard deviation sigma squared. So notice that nowhere it states that these are normal, because if these were normal, then we already know that y bar is normal and will be done. But here doesn't matter what distribution they have. If you define un to be this, which is what we call z before, then the central limiter says that the distribution of un, so technically un converges to a standard normal distribution as n goes to infinity. So therefore, if n is big enough, you can say that this will be normal regardless of what the original distribution is. Now, when we say n large, that's a little tricky to decide, but technically, if n is more than or equals to 30, the central limit term usually applies. So this is like the minimum thing. Now, what the central limit theorem says is this: look, if you have a distribution that is like exponential, clearly the graph for an exponential function, remember, look like this. Okay? So as you can see, 1 is not a exponential, but if you take a sample of 30 exponentials and you find the mean, so the mean of 30 or more exponentials, when you start doing the graph will look like this now. It's not quite normal, but it's looking more and more normal. So as n goes to infinity, so if n goes to infinity, so let's say this is for n equals to 30. So as n goes to infinity, this will become normal. And that's why the central limit theorem is such a big deal. Okay. For example, let's say the amount of caffeine in some energy drinks has a mean, which we don't know the distribution, we just know that the mean is, let's say, 80 grams, and the variance is equals to 10 grams. Okay. So again, remember, we don't know what the distribution is. So therefore, let's say that we take a sample of, I don't know, 36 energy drinks, a random sample. So what will be the probability that the average amount will be more than or equals to, let's say, 82 grams. Okay. So then we find the standard value on the side. So remember, un, I'm just going to call it z because we're going to use the normal distribution. So this will be y bar or minus mu divided by sigma, the whole thing divided by the whole thing times square root of n. So in our case, this will be 82 minus 80 times the square root of 36 divided by 10. So this will be 2 times 6, which is 12, divided by 10, that's 1.2. So therefore, this is the same thing as the probability that z is greater than 1.2. And if you look to the table, this will be 0.1150 or 51. All right, so let's look to the following example. So let's say that the fracture strength of tempered glass averages 14, which is measured in thousands of pounds per square inch, and it has a standard deviation of 2. So therefore, here we have the mu is 14, and the sigma is 2. So let's say that you have a sample of 100, and you want to find what's the probability that the sample mean or y bar will be more than 14.5. Right, so z will be the square root of 100 times 14.5 minus 14 divided by 2. So in this case, it will be 10 times 0.5 divided by 2. So this is 5 times 0.5, which is 2.5. All right, so therefore we're trying to find the probability that from here the z is greater than 2.5. So then you can look to the table or the calculator. You look to the table, the value from the table is 0.0062. So therefore the probability of this happening is 0.0062. All right, so let's say this is part A. So part B will be this find an interval. Okay. That includes with probability of 95, okay, or 95%, that the average, which means y bar, but the average strength of 100 randomly selective pieces of glass. Okay. Now there is more than one way to do this, but in essence what this is asking is the probability of minus a less than z less than a has to be 0.95. Okay. Now here you have to be careful on how to label this, because the table, remember, only gives you the area to the left. So therefore we want the area between here and here to be 0.95, which means that if you cut this in two, this one will have to be 0.475. Okay? And remember that the table will give you this value, and this value plus this value has to be 0.5. So therefore, this value here is 0.025. So that when you look to the table, that will give you a value of A of 1.96, which I believe we have done this before. So therefore, that means that 1.96 has to equals to y bar minus mu times the square root of n, or that was here, divided by sigma. So in our case, that means that 1.96 had to be equals to y bar minus 14 times the square root of 100, which is 10. So this is 10 divided by 2, which will give you 5. Because remember, this one is equals to 2. So therefore, if you divide by 5, you're going to have that y bar is equals to 1.96 divided by 5 plus 14, which is equals to 14.392. And if you do the same thing for 1.96, so similarly for 1.96, that's going to imply that y bar is going to be equals to 13.608. So therefore, the probability, the 13.608 is less than y bar less than 14.392 will be equals to 95%. So as you can see, these problems are straightforward, because what this means is as long as the sample is big enough, y bar is going to become a normal distribution, which means you can use the normal table to find the probabilities. And that's it.